I'm going to begin today by casting my memory back to earlier in the course when we had talked about energy, a number that you can calculate that has the remarkable property that it never changes or changes predictably. I can never get tired of saying that. We studied energy, kinetic energies, potential energies, and then at the very last of that discussion, we took an interest in the rate at which energy changes or is transformed, or I suppose in a sense transported, however you like to look at that. And this is the very slide. I went back, pulled the same slide again, gussied it up a little bit. But this is prior knowledge. Power is the rate at which energy is transformed. I have a tendency to use a backwards paragraph P for power. And when we first talked about power, I explained why. Capital P is also pressure. So if you have to do a lot of physics, particularly if you're designing a nuclear power plant, calling power capital P is going to be a problem. But here I can call it capital P, we'll agree. Capital P, the power, is the change in the energy over time. And so dimensional analysis-wise, that would be joules per second. But there's a common name for that, it's called the watt. So we just take a moment to realign ourselves to this idea of the rate at which energy changes. But I have to think about that in the context of the different kinds of energy that I have. I have, for example, kinetic energy. So when I talk about power, I could be talking about the rate at which the kinetic energy is changing. And at the time, the example that I used was, I'm driving my car and I put my foot on the gas and the power of the engine changes the kinetic energy of the car. I might even have questioned, in fact, I'm certain that I did, I might have questioned at the time, where did that energy come from? If suddenly the car has a number that I can calculate associated with the fact that it's moving, where did that number come from if I imagine that the energy is conserved? Well, the answer that I gave at the time is the chemical potential energy stored in the gasoline that was burned in order to make the go-go of the car. Let's imagine now in our modern times that I create a vehicle that runs not on gasoline, but on a battery. If I'm driving an electric vehicle and it still has an accelerator pedal, I hit that accelerator pedal, the electric motor in the car changes the kinetic energy of the car. So where does the energy come from? I'm no longer talking about the chemical potential energy of gasoline. If my electric vehicle has a very large battery in it, which it does, then what I'm talking about is the chemical potential energy of the process inside of the battery. I'm not talking about fuel energy. I'm not talking about gasoline. I'm talking about electrical energy. So apparently, the terminology associated with power also would apply to my electric vehicle. I also considered potential energy and used as my example that a crane could change the potential energy of an object. Say there's a high-rise apartment building, they need to put the air conditioner on top, so you get a big crane, you latch it on, and the crane does work to increase the potential energy. The power of the crane is the change in the gravitational potential energy over time. But when we first talked about this, I wouldn't have said, where did that energy come from? Because I would have had a little private secret in my mind. Where does the energy come from that the motor on the crane uses to increase the gravitational potential energy? Well, of course, that energy comes from the electrical effect. I already know from our discussion that there's electrical energy, and so today I want to discuss the electrical power. I don't need to derive any new equations from scratch. In fact, I really don't need to think that hard about it. I can work out everything I need to know about electrical power just from dimensional analysis. I mean, looking at the units of my physical quantities. Look at this. I'm going to make a claim that the power is equal to the current times the voltage. P is equal to IV. And you immediately burst into upsetment. Where did you get that from? You're just pulling equations out of nowhere. Well, actually, I'm not, because if you consider that how I have defined my current is a charge over time, and therefore current has units of coulombs per second, and the way that I've defined voltage is not the energy, but the energy per charge. When I multiply these two quantities, I have coulombs per second times joules per coulomb, and the coulombs will cancel, leaving me with a joule per second that is commonly known as a watt. All of our modern technology leverages the electrical effect to change all kinds of energy. As I pointed out, an electric vehicle can change the kinetic energy. An electric motor can change gravitational potential energy. As energy is transformed through the electrical effect, it suffers from the same downside as every other energetic process. Whenever electrical energy is transformed into other forms of energy, there is always a fraction of that electrical power that goes into generating thermal energy. I think you should be basically aware from being alive for this long that all electrical processes generate heat. It can be a problem. Your cell phone runs, it gets warm. If it gets too warm, you know something's up. All of the lights and electrical stuff in the classroom, they do fantastic technological stuff, computers and whatnots and iPads and things, and the fans that are cooling us down and the projector. But everyone knows that when you're using the electrical phenomenon to technological advantage, a certain fraction of that goes into generating heat. It's unavoidable. It's unavoidable. So of all of the energies that I can get, kinetic energy, gravitational potential energy, electric potential energy, all of these energies that I know of, thermal energy is also an energy that expresses itself whenever I try to do something useful with the electrical effect. Power is equal to the current times the voltage. Now that I have that, I can just get busy investigating all of our technologies and doing some calculations. I really have 3 power equations for you. No thanks, Charlie, I'm good with just one. Well, you are actually good with just one equation for electrical power. But as a practical matter, as students or professors or engineers applying these things, when you face a power problem, that is, you have some physical quantities, you're trying to solve for something that is unknown in the system, it's handy to have 3 different equations so that you can use the equation with what you have on hand. So it's true that the power is equal to the current times the voltage, but I also have Ohm's law, which is V is equal to IR. And what I'm going to do is jam those 2 things together and generate 2 new equations. It's easy to do. I'm going to have my equation power is equal to IV, but I don't happen to know what the voltage is. I just don't happen to know. In the problem that I'm solving, it doesn't tell me how many volts. And that's okay, because I'll simply replace the voltage in P is equal to IV with V is equal to IR. So it's IIR. That's weird. Power is IIR. That's weird. So I'll say power is equal to I squared R. That's another equation for power. It's absolutely equivalent, but it's the equation for power that I would use when I know the current and I know the resistance and I would like to know the power. I choose my equation based on what I know, what I have available. So maybe I have my power equation, power is equal to I times V, but I want to get rid of the I because I don't know what I is. Well, I can take Ohm's law and solve it. I is equal to V over R. And if I put I is V over R, that's V times V over R. That's weird. V squared over R. So the power is V squared over R. I have 3 equations for power that I can use depending on what I have available to solve the problem. Which equation to use comes down to what you happen to know. Believe it or not, the idea that I'm presenting you today, electrical power, is so familiar and so simple that I'm at the point where I'd like to engage an example. So the example that I have is a situation here where I have connected a 110 volt source, and I hope that you appreciate, there it is. That is the icon that stands for voltage, and it's 110 volts, which is conspicuous because that's the voltage of the outlet, between 110 and 120 volts. That's the voltage of an outlet that you plug stuff into. And then here you can see that I have plugged a 60 watt light bulb into the system. It could have been represented as a zigzag resistor, but I thought just for fun, I would use the icon specifically for a light bulb. This could easily have been a zigzag, and I would just simply have to imagine that it was a light bulb. Here it looks a bit like a light bulb, but you can see it's actually lit up. And it's a 60 watt light bulb. That's common, isn't it? If I go shopping for light bulbs right now, I have two options. I have LED light bulbs, which are much, much lower power, and the old-fashioned, I guess we're going to say that, incandescent light bulbs, among which 60 watts is a perfectly common choice. A 100 watt light bulb is very bright, maybe around my house. I don't want to be blinded everywhere that I go, so I choose a 60 watt light bulb. I do not typically have laying around my house, and that's a lie because of course I do, an ammeter to measure current. Most people don't. I have all kinds of scientific equipment in my house. Of course I do. Of course I do. It's like the bat cave in my house. But by and large, people don't have an ammeter laying around, but let's imagine that I do and I can measure the current. If I have 110 volts and I use it to light up a 60 watt light bulb, that is 545.89 milliamps is what my simulator says the current is going to, so that's my reading on the ammeter. And that makes sense because since the power is the voltage times the current, if I take my 110 volts and I multiply that current, it works out to 60 watts. So that's not much of a magic trick here. I convinced you that the current times the voltage was the power, and then I showed you that it is the power. That's not surprising at all. One thing I want to comment on here, by the way, is that that's 500 and some odd milliamps. That's half an amp. And so, I'm sorry, that's 0.5 amps. That's 0.5 amps. And so it is a relatively low current, a low danger sort of current situation. But that aside, I don't have an ammeter. And so I take a 60 watt light bulb and I plug it into an outlet and I wonder how much current it's drawing. I can't see the current. I don't have an ammeter. But what I can do is use the power equation that doesn't include the current. Here I'm demonstrating this strategy of using the power equation that gets the job done. I don't know what the current is, so I'll use the power equation that doesn't have current, which is V squared over R, and I'll do a little bit of stirring it around to solve for the resistance. Because I know that the voltage of the outlet is 110, and I read off the packaging that it's a 60 watt light bulb, and I discover that the resistance of that light bulb is 202 ohms. I can learn the resistance of the light bulb by understanding its power rating. A lot of the appliances and devices that we use in our everyday lives have a power rating on them. Read the label. It says how many watts. And based on the power rating, you can find out, depending on what information you have available, how much current it's using and what the voltage is. You can solve for any of the unknowns if you have but two of the knowns. And you can figure everything else out from there. And so understanding power is critically important to understanding our technology and the role that electrical effects play in it. But here's an important thing. If I see an object moving along at constant velocity, it has a kinetic energy that I can calculate. And so I talk about it in terms of the number of joules of kinetic energy that it has. If I raise a thing up to the 9th floor, I can calculate the gravitational potential energy. That's a certain number of joules that it has. When it comes to electrical phenomena run continuously. So the number of joules that are used when I'm working with an electrical system, the number of joules that are used depends on how long you let it run for. There's not a specific number of joules involved because the joules are constantly expressing themselves over time, which is why describing the behavior of technological devices and the electric circuits that they involve is most commonly done by describing their electrical power.
Mm-hmm.